So it is my pleasure to participate in this seminar in honor of Professor Julian Lavrinovich. And I am sure that every one of us have very good memories because of his hospitality, the very nice conferences that he organized there in Bedlewo, and he will always be in our memory. And now I will proceed to talk about my subject. As you see, the title is Hyperbolic Curves, an integration of bicomplex functions. So bicomplex numbers now we know a little bit because of the talk of Lino Resendis. So then I will skip a little bit this idea of the bicomplex numbers. So I use exactly the same notation as him. So they are numbers of this form, ij, the imaginary units. And something very important in my talk is that we consider the set of hyperbolic numbers because it is a particular case of the numbers in size of the bicomplex numbers. So we obtain hyperbolic numbers when Z1 is a real number and C2 is a pure imaginary number. So then that's why we obtain I times J. So then we obtain the hyperbolic unit. And also I want to make emphasis that because of the commutativity of the multiplication, it happens that the K square becomes 1. So then we have two imaginary units whose square is equal to -1 and K square is 1. And also, as Lino mentioned, we have these two very important that are the idempotent elements. This is the reason that they are idempotent, but they are also zero divisors. And they give us the opportunity to decompose every bicomplex number in idempotent form. Then also this idempotent form is very practical to perform the operations of sum, multiplication, division, and also help us to understand where are the zero divisors inside BC. Because we have to take into account that BC is also something real 4-dimensional. And it is direct proof that the zero divisors are they are in these two planes. They are complex planes. I mean, they are copy of C. I mean, and we usually use this notation. BZE is the set of all the numbers of this form. Z times the idempotent number E, and the set of C E dagger. Okay, so then there are two planes that live in R4 and they are orthogonal. They intersect only in 0. Okay, so then this means also that when we write the bicomplex number in the idempotent form, the first component belongs to BZE and the zero component belongs to BZE dagger. So then all the time we can have in mind where are the projections, because we can of course define the projections of the bicomplex number, and the projections goes to BZE and to BZE dagger. And also we saw that there are different conjugations. The idea of the conjugations, of course, is that because when we are developing a hypercomplex theory, we try to understand which properties of the complex numbers we follow. Because in the case of complex numbers, the conjugation is important because it is related with the Euclidean norm. So then it happens that we have different, but I will tell you that the one that is important to us is what we call here, you see, C star. C star is defined in this form. So of course, the definition of the conjugation does not depend on how we write the bicomplex number. But when the bicomplex number is written in idempotent form, C star is written as you see here, beta 1 bar E plus beta 2 bar E dagger. And the product of C, times C star, we obtain an element as you see here. A modulus of beta 1 square E plus another element beta 2 modulus square E dagger. And it happens then that both components are positive real numbers, or 0 in the case that Z is equal to 0. And then here comes the set D plus. Who is D plus? D plus is the set of hyperbolic numbers such that when we write them in idempotent form, both components are positive or 0. And in other words, here I have the figure. So this is the plane R2, but it is endowed with the structure of hyperbolic numbers. So then you see, here is the number 1, K. Here is the line where is the idempotent E, and here is E dagger. So then here in this plane that we see the hyperbolic numbers, this cone to the right is the set of positive numbers. And of course, we can define that the cone, the opposite cone is the set of negative hyperbolic numbers. So then one of the aims of my talk is to talk about the geometry, because immediately we begin to define many geometrical objects. So as we see now, as Lino mentioned, also we define a partial order. So I only recall that this is the notation. 2 elements in D, if the difference belongs to the plus, then we say that C1 is small or equal to C2. And we denote with this symbol the new partial order. Then an important property of this partial order that in particular, when we restrict to the real numbers, it happens that this partial order extends the total order defined already in R. And here is an illustration how we can see the numbers that are related with a given hyperbolic number ZZ, Z0. So then you see, here is Z0. And the idea is that as we translate the cones of the positive and the negative numbers, we translate to this point. And then what is here are those who are larger than him, and here are whose are smaller. And of course, the numbers that belong to the upper and lower cones, they are not related with Z0. So then, as we mentioned before, we have that Z times Z star, we have here some square. Maybe I will come back a little bit here. So then we see that we have C times C star. We obtain this module square E plus this module square E dagger. There are many properties of the hyperbolic numbers that are well known since many years ago. So then it is possible to take the square root of them, and we can take the positive square root in each idempotent component. This positive square root is which one defined here as the hyperbolic valued modulus. So this is also something new that we define in this book together with Alpay, Strupa, and Shapiro. And then we have that this model is hyperbolic valued. And thanks to the partial order that we defined, it deserves to be called norm modulus, precisely because it has all the properties that are necessary. So then we can get the triangle inequality also. So then now that we have this this modulus, hyperbolic valued modulus, a very good property that it has is that in the case that our bicomplex number is a complex number, then this modulus, hyperbolic valued modulus, becomes a real number which coincides with the usual complex module of a complex number. So then it extends the modulus of complex numbers. Okay, now something more, another geometrical object is the hyperbolic interval. A hyperbolic interval is defined as follows. Let's take two hyperbolic numbers, A and B, written in idempotent form, both the numbers. And then also we choose them such that A is related with B with respect to the partial order. Then the hyperbolic interval is given as the set of all the hyperbolic numbers such that their idempotent components they give this, we have these inequalities. Nu one is between A1, B1, B2, B1, and nu two is between A2, B2. So then, now I will give something more about the interval. This is a hyperbolic interval. And also we can talk about the length. We define the length of the interval just like we do with the real intervals. The length of a hyperbolic interval will be just the difference between between B and A, B minus A, which will always be a positive hyperbolic number. So here I have the interval. This is an interval. And you see, I wrote here a non-degenerate hyperbolic interval. Why non-degenerate? Because in the case that the difference B minus A will be a zero divisor, we will obtain only a line, a usual line. So in this case, we not consider this as an interval. We will work only with non-degenerate intervals. This means that an hyperbolic interval has to be something real two-dimensional. Okay, now, as you remember, the title of my talk is related with integral. And in the real case, the integral is related with make measure of something, right? For instance, when we teach to the students of calculus, the Riemann integral, they know that the integral of the constant function one, on one interval AB, will coincide precisely with the length of the interval. So then, the integral that I am looking for are those that behaves properly well with the notion of length of hyperbolic interval. So then that's why now I give an example how it happens that this partial order that we have defined, we can say that it gives us a weird behavior about the notion of the hyperbolic length. What do I want to say? I want to say the following. This is a question. If I have a hyperbolic interval I, and I subdivide into subintervals I1, I2, In, what should I expect? That the sum of the lengths of the subintervals will give me the length of the total interval, right? And it happens that our definition of length of interval does not behave well with this idea. So this is what the answer to my question is no. And here is an example. I took only two different hyperbolic numbers related with the partial order. I took C equal to this number and W this number. So it happens that W is larger than C with respect to the partial order. Then the length of this interval is this number 9E plus 5E dagger. Now what we do? Subdivide the interval in different subintervals, as I do here. And I can tell you that if I find precisely which are these numbers and I consider the length of each subinterval, it happens, I wrote here, Each interval are those, these are the lengths. And it happens that the sum of these lengths does not coincide with the length of the interval. So then this means that we have to think in a different way about the geometry that we are using. And in this paper, together with Balankin, Bori, and Shapiro, we gave this theorem. The theorem tells us when everything works well with respect to the interval and when we subdivide. So if we take a non-degenerate interval and we take a finite subset of it, this is the finite subset, and this subset satisfies the following conditions. S is a chain. So this means that it is a totally ordered set. This is what I am writing here. And the first Z0 is equal to Z, and the last element is equal to W. These are the conditions. The other condition is that the difference between two subsequent Z is not a zero divisor. Then in this case, yes, it happens that first of all, we define then different subintervals of the original interval. And in this case, yes, we have that the length of them will coincide with the length of the original interval. Okay? Now I will explain, because when we obtained this result, I was thinking, which is a justification of this fact? And I arrived to the following conclusion. So this is the interval in which we start. I will build the chain that I mentioned, the numbers Z0, Z1 until Cn. So to obtain C1, what do? I consider the cone of those numbers which are larger than Z, the first number, Z0. So then inside this set, this cone, I will choose C1. And I continue in this way. What do I want to say is that now I stop in C1, I consider the cone of the future of him, and there inside this cone, I will choose Z2, and I continue in this form. After Z2, we choose Z3, Z4, and in this case, I wrote C5 equal to W. And the justification of this is that when we want to measure something, and also we know from physics that this cone, for some reason, is called the cone of the future because we know that these lines in this cone is the limit of the speed of the light. So then this means that if we want to make some measurements with respect to this new geometry that we are developing, we cannot make measurements in the past or to make a measure in something that needs for me to move faster than the speed of the light. So then that's why if I want to make the measurements, I only can go to the future. So then for the moment, this is one of the justifications that I can find. And then I can build these subintervals. And only in this form, I will subdivide the interval and everything works well. So then with this idea, because I have only a few minutes, becomes the definition of the integral. So then the integral first, I will consider only for functions from D to D, because I want to tell you something else. In the theory that we are developing, it happens that the set of hyperbolic numbers, they play a very similar role. Okay, I will start. The role that the hyperbolic numbers play inside the set of bicomplex numbers is similar to that real numbers play inside of the set of the theory of complex numbers. That's why many times we realize that the hyperbolic numbers behave like real numbers. So then we have hyperbolic lines, hyperbolic Veiled modulus, the order is given initially in D. So then that's why if we want to understand perfectly well, which is the integral that we will use in the bicomplex numbers that will behave well with this new geometry, we have to start with the case of functions from D to D. That's why the idea that I mentioned before, I will give you only very briefly, I have 4 minutes, which will be the starting point to define the integral. Because then if we start with an integral, we give a partition. We need a partition. A partition will be precisely a set of totally ordered points inside the interval. So that this means that they are totally ordered. And also we can, in each subinterval, we can take a given point. So then we can label, or we can have a labeled partition. And also we can consider the diameter of the partition. And when this definition is the starting point to define the Riemann sum, because if now we have a function defined in the given interval, and the values of the function is hyperbolic, then with the elements that I have given, we can define the hyperbolic Riemann sum. And then we can give the definition of the hyperbolic Riemann integral. So then we will have a number, which will be a hyperbolic number, such this will be the integral of the function if for every epsilon positive and non-zero divisor, there exists a hyperbolic positive number, non-zero divisor, such that if a target partition, as I define it, which diameter is smaller with this partial order, smaller than delta, then this inequality will happen. So then with this definition, it was possible to give the first theorems that are required to develop the theory of the integrability of functions from D to D. So I think my time is over because I wanted to mention, for instance, it is proved that every constant function is integrable with this definition. Also, every continuous function that is not necessarily the idempotent components, not necessarily of the form of product type. I mean, the first component can depend of both real components, and the second component also depends of two variables. So it is possible to define the integral of a continuous function in general. And this is what I wanted to say. So I will go to the end and to give thanks for your attention because I think my time is over. Thank you very much.
Okay, thank you. Any questions or comments?
Okay, here is Lino. Marilena, thanks
Yes.
a lot for your very nice presentation. I have
you.
learned a lot about your presentation. And also, I would like only to make some remark. I think that in this moment, you can show with your talk that there is a lot of hidden geometry in this bicomplex structure. In particular, hidden because it's hidden because these hyperbolic numbers are hidden in the bicomplex structure. And I think that this is one of the difference with another complex structure. Moreover, for me at least, it's more easy to see the geometry with this bicomplex structure. In particular, with these hyperbolic numbers. Thank you very much.
Yes,
and
maybe
best regard for Michael, please.
Thank you very much. Maybe if I can say something else, precisely related with the questions that were made during the talk of Lino. The composition of the bicomplex holomorphic functions given in two parts, a very formal proofs of these facts were given by Bailey Price in a book that is very classic to those who study this theory. But I want to mention that in this book, very excellent book, the author never mentioned the hyperbolic numbers. So then this is in the moment that we found that the hyperbolic numbers plays this crucial role and give us a lot of geometrical information. Now we can give with the new eyes this theory, because I can tell you honestly that many times we receive the comments that it's only 2 copies of the complex theory and that's it. And this is not the fact, because really we are finding more and more new facts and that can be explained with geometric hyperbolic objects. Okay, thank you.
Okay, thank you.